All right, here we are for part 3, and I want to continue on discussing steel beam design aids. So this is part 3 of lecture 13 of CENG 4412, Steel and Concrete Design. Okay, so I want to look at the design aids or the design tables for beam design that are present in the AISC steel manual. So let's look at design tables. Now, in the code, or what we've looked at previously, we've looked at the actual equations that you're going to use, the actual equations that are really the fundamental, very basic level, or the truest level of what you're using to actually calculate your capacities. However, there are a series of design aids or design tools that allow you to more quickly arrive at solutions if you're operating in certain regimes with certain assumptions, that sort of thing. So design tables are very useful tools, not necessarily for analysis, but at least for design, for selecting a particular shape. The design tables can be invaluable. So design tables. So here, now if I look at, say, section, these are found in chapter 3, a series of tables on that aid us in calculating beam capacity. So basically, you've already seen so far that calculating beam capacity for steel beams can be quite involved. We have to worry about lateral torsional buckling, we have to worry about local buckling, we have to worry about all of these things. And so if we can have some pre-made calculations effectively, that can really help us move through things a bit quicker. So table 3.1, this is going to be something that helps us, essentially it's a table of pre-calculated CB values. Table of pre-calculated CB values. And this is on page 3-18. Page 3-18. Now, however, this does give us our very first cautionary note about using design aids. So, what do we notice? What does it say right across the top of that table? What does it say right at the top of that table? Simply supported beams, yes. At the top of the table, it says table 3-1, values of CB for simply supported beams. So, note, this table is only valid for simply supported beams. And I like beginning this explanation of this particular table because its limitations are readily apparent just from the top title there. These CB values are pre-calculated for some typical loadings that you often have on simply supported beams. However, if you try to use this for any other type of support, for a cantilever beam, for a cantilever beam, for a fixed beam, a fixed pin beam, anything like that, if you try to use this for that, you will end up with the wrong CB value. And if you do, you can end up really hurting yourself or somebody else. So, this really gets at the heart of this. One of the core lessons for today is that, you know what, in fact, I might even write this in a different color because this is important. Design aids are dangerous. They are dangerous. To a certain degree, they make things too easy. They are dangerous. They at times can lull you into a false sense of security or a false sense of confidence, maybe not security, but confidence, in terms of thinking you actually know the capacity of something when you don't. The key to using these, is that you need to be aware of what assumptions and limitations go into this design aid. You must be aware of what assumptions are going into this table. are baked into this table. If you're not, you're going to have a bad time. So, or in other words, you're going to calculate its moment capacity wrong. You're going to do something either. Now, this could go either way. You could end up vastly overestimating or vastly underestimating a beam's capacity, and really each of those are bad. Now, obviously, underestimating a beam's capacity underestimating a beam's capacity just means that you're going to end up with something heavier than it needs to be. Overestimating those where it gets really dangerous, because that's where you can actually have catastrophic failure. So again, you must be aware of the limitations and assumptions present in whatever design aid you are using. Okay, so with that in mind, next I'd like to look at Table 3.2. That'll be another very useful one. Table 3.2. 3.2. Is beam selection by ZX. Now, what's interesting about ZX is that this is your, again, that is your plastic section capacity. That is your plastic section capacity in, your plastic section modulus. So again, so this is a section property independent of material. However, so basically, we do know, however, that ZX loosely corresponds to bending capacity. Not directly related, but you also need to consider buckling and things like that, and buckling and material strength and things like that. But ZX is loosely proportional to bending capacity. Thus having shapes sorted by ZX can be useful. All the W shapes sorted by ZX can be useful in finding the lightest shape to carry your load. By ZX can be useful. Can be very useful. And then also it has, this table has a series of bold and then non-bolded numbers in groups. The bold and non-bolded basically what that means is the bolded will be the lightest in that group. So for example, if I look here, for example, I have, and I'm going to try to write this in bold here, which is harder with a pen. So maybe I'll do like this. For example, looking on my manual, I have this kind of thing here, bolded, W 40 by 431. It's very hard to do bold in a pen. By 431. And then below that I have W36. 36 by 441. W 27 by 539. And W 14 by 808. And then the corresponding ZX values for these. The corresponding ZX values for these are 1960, 1960, 1910, 1910, then 1890 and 1830. And the purpose of this is to show that, yes, well, the whole table is sorted in descending ZX values, but the point here is that, look, this is the lightest. The bold is the lightest. So if all you're concerned with is weight, now, you don't necessarily want to always use the lightest because in this case it's also the deepest, so maybe that wouldn't be beneficial depending on your geometric constraints, but this is going to be the lightest. The bold indicates the lightest in a particular group. So in other words, if all you're concerned with is bending moment and weight, in that case, you would never use the 36 by 441, 27 by 539, etc., because this particular one has higher bending moment capacity and lower weight than each of these. However, though, it does have a larger depth, so that may not be beneficial. So it is sorted by ZX, but also you can see here that this table provides many other values as well. So what else does this apply or provide? Table also provides a variety of section properties, or a variety of capacities, I should say. Is sorted by, again, table 3.2 or 3-2 is sorted by ZX, but also provides a variety of other things. A variety of capacities. A variety of capacities and other things. A variety of capacities and useful calculations. And useful quantities. So look what it provides. First of all, for a given shape, it's going to provide LP, LR, LP and LR. That is exceptionally useful, because we've seen previously what a pain in the butt it is to calculate LP and LR, and to have it just outright given to you, suddenly that's very, very useful. Suddenly that's extremely useful. However, though, we do, of course, so just look at that. Looking over there, we see that we have our LP and LR values just given to us. That makes things so much more useful, or so much easier. And also, in turn, it gives us phi MP and phi MR. Wow, look at that. Isn't that great? We can just actually outright get our bending moment capacity based on that. So, so for example, it gives us our phi B, MR, that sort of thing. Or phi B, basically we have our phi MP, that's going to, or as the manual here says, phi B MPX for our LRFD. So for example, it has phi MPX, that's basically saying plastic moment capacity in the X, and it also has, say, phi MRX, the residual moment capacity in the X direction, strong axis bending. And it just gives it to us. We don't even have to do a single calculation. It just outright gives it to us. However, though, we do have an issue. Here, though, as I mentioned before, what do we have to be very careful with these tables? Why are they dangerous? Assumptions, yes. So they just give us these things that, remember how hard it is to calculate the LP, the LR, how involved that calculation is? They're just giving it to us. And so this does make things very easy. Very easy. However, they're also dangerous. Again, because of the assumptions. Because of the assumptions intricately baked into this table. Baked into table. Namely, you can see here, for this particular table, the assumptions are going to be as follows. They're going to be based on, for this particular one, Fy is 50 KSI, Fy is 50 KSI, and our CB is 1.0. And our CB is 1.0. So let's see here. Again, this is based off of CB of 1.0. Okay, here, let's see. Now, let's see. Now we also have another very useful thing provided, and that is the beam factor. So let's describe how to use this here. So I'll provide another warning here. Another equation that you'll want to be able to know how to use. Note equation 3-4a on page 3-10. On page 3-10. Know how to use this. No, you must know how to use this. You must know how to use this. And so, again, you cannot simply assume. Do not simply assume ever. Do not go blindly to your, I shouldn't even say simply, I should say blindly. Do not simply blindly go to your section and assume that is your capacity. And assume that's your capacity. Is your capacity. And we have a value for beam factor, BF, is equal to MP, MPX, and this is found in, this is equation 3.5 here, another equation, 3.5. The beam factor is equal to MPX minus MRX divided by LR minus LP minus LP. And you can combine this along with equation 3-4a to handle something with a CB other than 1.0 here. But again, this is kind of very similar to, basically this is kind of, this might remind you of an interpolation effectively. So 3-4a for LRFD is like this. Phi BMN is equal to CB times Phi B, or Phi B times MPX minus Phi B times the beam factor times LB minus LP. And then close bracket here. And then this looks very similar to an interpolation, but basically, in short, table 3-2 is very useful, or can be used if your length is less than LR. If it's not, then you really can't use it. If it is, then you can use it. But if it's not, then you're going to have to use the longer form equation longer form equations present in chapter section F2, chapter F, section 2. So again, this was very useful if you're in that range. It can allow you to very quickly sort of converge on a solution. Allows you to spend less time iterating, that sort of thing. But you do have to be very careful with it. So. Let me work through a brief example here. So here, example. let us say I have a, here, given, I have an ultimate factored load of 1,000 kip feet. I want to design a beam with an ultimate factored load of 1,000 kip feet, and LB is equal to 15 feet, and FY, the material I'm going to be using, is 50 KSI. 50 KSI steel. And then find, so this is given, and then I want to find the lightest section to carry load. The lightest section to carry the load. So here, now let's see here. So if I'm looking here, back here, let's see. So we need to find a section to carry this load. And let me find, I have a citation here. I'm trying to find where this is in the manual, just a second. Phi MP of 1,060. Here. Yeah, 1,060. Yes, okay. And so I need something, I want to find the lightest section to carry the load. So let me do that. And I'm going to use table 3.2 to do this. I'm just going to go ahead and say, hey, let's try a W30 by 90. And how would I find that? Well, I know my phi MP is going to be, needs to be 1,000 or greater, and I know my capacity needs to be 1,000 or greater. So maybe I'll go over to, I'll look in table 3-2, and if I'm on page 3-24, as I look up, I see that if I'm looking in the third column there, or I guess fourth column, the phi B MPX, the plastic moment capacity there. And I see that that group of sections is where that number crosses over 1,000. And I could use any of those, but of those, the 30 by 90 is going to be the lightest one. So let's try that one. So let's see what this gives us. Well, 30 by 90. So we have that, and it tells us a few section properties. It tells us that LP here, 30 by 90, is equal to 7.38 feet. So from the table, and I do know, of course, that I can use this table because I'm dealing with an Fy equal to 50 KSI. And I'm looking here, I can see that LP, the plastic length, is going to be equal to 7.38 feet, and LR is going to be equal to 20.9 feet. And then I also know that phi MP is equal to 1,066 kip feet, and phi MR is equal to 643 kip feet. Now, it may seem like I'm fine. I mean, if I'm looking here 1,000, then obviously 1,066 is greater than 1,000, but we have to be very careful. Look here. What is our brace length? Our brace length is actually 15 feet. In this case, our LB is going to be greater than our LP. Uh-oh. For us, for our case, LB is greater than LP, but less than LR. So that means we're in that intermediate range. We're in the middle range. Before the residual moment, but beyond the plastic moment. And we discussed this previously. So because of that, I'm not going to get the full plastic moment capacity. I'm not actually going to get this full capacity here. So instead, I'm going to interpolate between two, I'm going to use these as data points and interpolate between them. So I have 2 points. I have the point 1066, or actually the point 7.38, 7.38 comma 1066, and then I have the point, that would be 20.9 comma 643, and then I'm going to interpolate between them, and then I have a linear equation describing the capacity between them. And then I'm concerned with a brace length of 15 feet. So you can just use linear interpolation to find this, and when you do, if you interpolate, you will find that phi mn, in our case here, is 825 kip feet. I'm not going to get the full plastic moment capacity. I'm between the plastic and the residual, so I'm not going to get that. This is actually less than 1,000. This is no good. We're going to have to go back to the drawing board. No good. We're going to have to try again. So I'm going to have to try something else. I'm going to have to go to a deeper section, and I'm going to go to the section higher, I believe. So let's look here. Or let's see. In my notes here, I have trying 30 by 99. Let's see that. 30 by 99. Is that here? That's equal to 1170. Yeah, 30 by 99. That is in the next group higher. So basically, if I don't find a capacity in that particular group, I don't want to try one of the ones below. I'm going to try to go to the next group higher. So I'm going to try a W 30 by 99. In this case, LP is going to equal 7.42 feet. LR is equal to 21.4 feet. Phi MP is equal to 1170 kip feet. And phi MR is equal to 919 kip feet. And if I interpolate this time, I get that phi MN is equal to 919 kip feet. And again, we are no good. This is not going to work. This is still not going to work. So I'm going to try a third time and go to the next higher group, a W 30 by 108. 30 by 108, and here, LP is going to be equal to 7.59. 7.59 feet. LR is going to be equal to 22 feet. And phi MP is equal to 1,300. And phi MR is equal to 785 kip feet. Kip feet and kip feet. And this time when I interpolate, I get something good. I get that phi MN is equal to 1,035 kip feet. And this will be good. So, just in this brief example, we see how useful these design cables can be if you know what you're doing and you're using it properly. I was able to quickly jump through the moment capacity of 3 different sections. Imagine how long it would take to do all of those using just the equations from the chapter F section 2. That would be very, very long and very, very tedious. But if you know what you're doing and you're doing it properly, you can use this to very quickly jump to a allowable capacity, assuming you have 50 KSI material, etc., etc. All right, questions on how I did that? Okay. So then I'd also like to just mention another table. A few other tables. There are many other tables here, but just wanted to mention one. 3-10 is this, but in more graphical form. Table 3-10 here. Table 3-10, what is this? This is the available moment capacity as a function of unbraced length, but plotted for each beam. Basically, this is a great big graph, but fitted onto a series of sections. onto a series of pages. It's basically one continuous graph, one very tall graph, really. This is the available moment capacity versus unbraced length. Versus unbraced length. And again, we have to be aware of assumptions. Note, as it indicates, this is based on CB being equal to 1.0 and FY being equal to 50 KSI. 50 KSI. And here, shaded sections are lightest. Just like we have dash, just like we had bold before, here we have shaded or solid, solid lines, I should say, not shaded. Solid lines are the lightest, and dashed lines are the non-lightest for a given unbraced length and capacity. So the question is, if this is the lightest section, if that's how we can find the lightest section, why would anyone ever deliberately use a heavier section? Yes, typically size requirements. Yeah, that's what it usually is going to come down to. If you look, typically, if you have often heavier sections are needed because of sizing requirements, in particular, depth requirements. Are used to meet depth requirements. I may not want a 40-inch deep beam in my building. That's going to take up a lot of headroom. And so that's going to take up a lot of headroom, and often it may be beneficial to use a heavier section, even if it's more steel. Often it can be beneficial to use a heavier section simply to save up on all of that otherwise taken up space. Often heavier sections are used because they are not as deep. And this isn't also about just architectural requirements. If you think about it, the depth of the beam, now, yes, we could always just say, oh, let's just make our building taller. We could use a really deep beam, and then we could just have, a little bit higher stories or something. Well, what is the problem with that philosophy? What's wrong with just saying, okay, well, I'll use a really deep beam and I'll just make my stories a little bit taller? What's the problem with that?
Code requirements.
There are code requirements, yes, that's true. But just from a structural point of view, wind loads, exactly, yes. So I can make my beams really, really deep. But in turn, the problem with that is, as my building gets taller, it's going to be self-defeating at a certain point, because I am then going to end up gathering more wind load, and that means my columns are going to have to take more load, et cetera, et cetera. All of this is intertwined, as you've probably already seen in some of your design work before. Okay. All right, and that's briefly what I want to cover on design aids. Although I think, and then there will be a fourth section here. Oh, actually, there is one other thing I want to mention that isn't strictly related to this kind of beam design, but a lot of students do find this exceptionally useful, and I use this a lot myself. It's one of my favorite little tables in here. It isn't really strictly related to beam design, but it is still incredibly useful. Isn't strictly related to steel, but it is incredibly useful for beam design. And Table 3-23, basically this is just a big table of pre-made, pre-calculated shear and bending moment diagrams. This will be exceptionally useful, especially on a timed environment like an exam, for example. Pre-calculated shear and bending moment diagrams. Pre-calculated shear and bending moment diagrams. So, and again, the important thing to be aware of, though, is we have a whole bunch of different support conditions. You need to make sure that you are using your appropriate support condition for the beam that you have. All right, but yeah, many students do find that exceptionally useful, and as you're going through some of your homework and things, you'll probably find those useful as well. All right, so that'll do it for now. That'll do it for this part of the lecture, and I'll cut off here, and thank you.